Alright, we are looking at chapter 4.1, which is rational expressions. So what are rational expressions? What are rational numbers? Well, rational numbers are essentially fractions. So we'll be doing a lot of fraction work in this chapter. So I'd advise maybe refreshing yourself on some fraction work. But rational numbers in terms of 30-2 is we're actually looking at rational expressions. So what are rational expressions? Well, a rational expression is an expression that has a polynomial for both the numerator and the denominator. So we're combining polynomials and rational numbers. So for example, 2x divided by 3x plus 4 is a rational expression. We're also going to take this rational expression and eventually look at rational equations. But for now, let's just focus on expressions. Okay, so how can we write rational expressions? How can we create rational expressions? So Josephine is an accomplished long-distance runner on her school track team. She has completed 3 kilometers of a 10-kilometer race in 15 minutes. She wants to finish the race with an average speed of 0.25 kilometers per minute. So to determine the time in minutes that Josephine must run the remaining 7 kilometers. Alright, so first of all, realize that your book might do this a little bit differently. So I want to run 0.25 kilometers every minute. Okay, so we need to realize how do we state speed? Well, speed is equal to distance over time. We can create this formula by just looking here. This is distance over time, gives us our speed. So we want our average speed to be 0.25 kilometers per hour. So we want 0.25 to equal our distance. Well, what is our distance? Our distance is 10 over our time. So what we need to look for is that time that will make us have this average speed of 0.25. Well, we already have part of our time. Part of our time is 0.15 minutes. So we can rewrite this as 0.25 kilometers, that should be per minute, is equal to 10 kilometers divided by 15, the time we've already run, plus the remaining time that we'll need to run the race. So this is a rational equation that represents this. So we want to run 10 kilometers total. We've already run 15 minutes. We need to run some more time. At the end, I want to know what time that would be that would allow me to have an average of 0.25 kilometers per minute. So how do we solve this then? How do we solve how much time we need, or how fast really we need to run in order to finish with an average speed of 0.25? Well, we want to isolate t. So 0.25 is equal to 10 divided by 15 plus t, and we want to isolate t. This is going to take a few steps. I'm going to start by multiplying both sides by 15 plus t. 15 plus t. What this does to this side, it gets it off the bottom. So over here we'll have 15 plus t times 0.25 is equal to 10. Now I want to continue to isolate t, so I'm going to have to use my knowledge of bed mass. So I'm going to divide both sides by 0.25 by 0.25 to get 15 plus t is equal to 10 divided by 0.25. Well, what's that on my calculator? So 10 divided by 0.25, so equals 40. And then I want t by itself again, so I'm going to subtract 15 from both sides, meaning that t is equal to 25. So if I finish the second part of the race, the last 7 kilometers of the race in 25 minutes, I will have an average speed of 0.25 kilometers per minute. Well, let's confirm that. So 10 kilometers divided by how many total minutes? Well, 25 plus 13, 25 plus 15, which is 40, should equal 0.25. 10 divided by 40 is 0.25, meaning that t equals 25 is in fact my solution. So then I can write the solution to my word problem. What's her name? Josephine would need to run 7 kilometers in 25 minutes in order to have an average speed of 0.25 kilometers per minute. Alright, something you need to realize about this chapter is, and it kind of bothers me in the book, is that they actually start with harder concepts and then kind of go to easier ones. So just again, make sure you're always trying to figure out those basic numerical ones and then moving on to the word problems. You should have enough information from previous years of math to be able to look at this and understand it. It's just that I don't think it's ordered the best. Okay, so let's create another rational expression. All we're doing is creating that rational expression. We don't necessarily need to solve it. So one hose can fill a swimming pool in Y hours. So one hose can fill a pool in Y hours. A larger hose can fill the same pool 20 minutes faster. So before we even move on, how can we state that? Well, a larger hose, we'll put large hose, small hose, fills it in Y hours minus 20 minutes. Alright, so this is how we can state that information. That being said, right now we have kind of a disconnect. We're using hours and minutes. So let's convert this Y into minutes. So Y hours, so 1 hour would be 60 minutes. So instead of saying Y hours, we're going to say 60 times Y hours is our minutes. So our large hose actually fills the pool in 60 Y minus 20 minutes. Well, how does that work? Well, if it filled it in 2 hours, it would be 120 minutes minus 20 minutes. The small hose would be 60, so 2 hours would actually be 120 minutes. Okay, so we've just converted this all to minutes. Now, write an irrational expression for the fraction of the pool that is filled by the larger hose in 1 hour. We need to be careful because we changed everything to minutes, so in 1 hour we're actually looking at 60 minutes. So think about it this way. If we're using the small hose, and it takes 4 hours to fill the pool, well, that would be 60 times 4, so 240 minutes to fill the pool. But we're only using the hose for 1 hour, or 60 minutes. How much of the pool would be filled in 1 hour? Well, 1/4 of the pool. Okay, so I'm just kind of trying to base this all on some logic, some thought about the entire process. So what about the large hose? Well, the large hose will fill the pool in 60 Y minus 20 minutes. So 1 hour would be 60 minutes. So this is a rational equation that represents the amount of the pool that would be filled in 60 minutes. That being said, we should always reduce. So what can we reduce this all by? Well, let's divide everything by 20. We get 3 over 3y minus 1. So in 1 hour, this is the percentage or the fraction of the pool will be filled. So it might, so if it actually took 4 hours or it took 5 hours, we don't know. All we're saying is in 1 hour, this amount of the pool will be filled. So then if we had elaborated on the question and said, well, it takes 5 hours for the large hose to fill the pool, well, that would mean in 1 hour, it would be 5 times 3 is 15 minus 1, 3/14 of the pool would be filled. All right. I know those can be a bit tough, so just make sure you're working along with the examples, emailing me if you have any questions. Now, before we move on, let's look at something called non-permissible values. Non-permissible values are values that variables cannot be. So what we need to remember is that in a fraction, we cannot divide by 0. So let's look 4 divided by 0. That's undefined. We can't do that. 16 divided by 0. We can't do that. So a non-permissible value is a value in an equation, or rather in a rational expression, that would make our answer undefined. So when 4 divided by x, we can't have that denominator equal to 0. So x cannot equal 0. 0 is our non-permissible value. In 4 divided by x plus 1 cannot equal 0. So therefore, whatever value of x makes x plus 1 equal 0 is our non-permissible value. In 4 divided by x squared plus 2x plus 3, x squared plus 2x plus 3 cannot be 0. That being said, can a denominator be a positive number, a negative number? Yes, it can be any number, but it cannot be 0. So let's practice that then. State the non-permissible values for each expression. So our first one is 5 plus x. Alright, so 5 plus x over x plus 2. All we need to do is realize that the denominator cannot equal 0. So x plus 2 cannot equal 0. So what I do is I just write the equal sign with a cross out of it, meaning cannot equal. Then I isolate x by subtracting 2 from both sides. So x cannot equal negative 2. Why? Well, if x equaled negative 2, we'd end up with 3 over 0, which is undefined. So my restriction in this case is x cannot equal negative 2. Alright, what about 3 plus x over x squared? Well, in this case, x squared cannot equal 0. Well, how do we solve for x? We just want to isolate it, so we square root both sides. X cannot equal the square root of 0. X cannot equal 0. 4 over 12 minus x. Well, 12 minus x cannot equal 0. In this case, we want to isolate x by adding x to both sides. So this is just algebra. 12 cannot equal x, because if x equaled 12, our denominator would equal 0, and we would not have, what am I trying to say? Our denominator would equal 0, and therefore we would have an undefined answer. Finally, negative 15 over x squared minus 5x. This is a tough one. X squared minus 5x cannot equal 0. In this case, what we'd have to do is we'd have to take x out. So x minus 5 cannot equal 0. And this is a bit tougher. So realize that we have two factors here. We have a blue factor and a pink factor. If the blue factor equaled 0, no matter what the pink factor would equal, we'd still have, our equation would still equal 0. So if the pink factor was 4 and x was 0, 0 times 4 is 0. So what we need to do is break up our two factors. X cannot equal 0, and x minus 5 cannot equal 0. Well, here is our first non-permissible value. Our second non-permissible value is going to come from this second factor. So we're going to add 5 to both sides. X cannot equal 5. Therefore, we would state this: x cannot equal 0 or 5. Okay? So, what I want you to do now is write a rational expression that has a non-permissible value of minus 2. And there are a variety of different ways. I'm going to give you just a couple. So, any number on top, x plus 2 on the bottom, x cannot equal negative 2, because if we plug that negative 2 in, our denominator would be 0, and therefore we are wrong. So realize that any variation of this, so 16, 160, 2160, no matter what, as long as you have x plus 2 in the bottom, it answers this question. What's another one? Well, what if we had 4 plus x over x plus 2, x minus 1? Well, in this case, x cannot equal -2. And of course, there is a second restriction, but we have a non-permissible value of -2 either way. So there are a variety of equations that have -2 as a non-permissible value. All right, now let's look at equivalent rational expressions. So this is building off the concept of equivalent fractions. So we'd have 1/2. What are equivalent fractions of 1/2? Well, we can multiply the top and the bottom by 2 to get 2/4. We could also multiply the top and the bottom by 3 to get 3/6. We can multiply the top and the bottom by 100 to get 100 over 200. And all 4 of these are equivalent fractions. They all equal 1/2 or 0.5. So we're applying that same concept now to rational expressions. All right, so what is a rational number that is equivalent to 8/12? That's the same process. We could just multiply the top and the bottom by 2, 16 24ths. But what we need to realize is we're creating equivalent fractions by multiplying the top and the bottom by the same number. We could multiply the top and the bottom both by x. So 8x over 12 is equivalent to 8 over 12. Sorry, 8x over 12x is equivalent to 8 over 12. So let's find a rational expression that is equivalent to 4x squared plus 8x over 4x. Well, as long as we multiply the top and the bottom by the same number, we're going to get an equivalent rational expression. So let's multiply both by 2. We would have 8x squared plus 16x over 8x. These are equivalent rational expressions. Let's multiply the top and the bottom by x over x. Well, this will equal 4x cubed plus 8x squared over 4x squared. Again, these are equivalent rational expressions. Now, why can we multiply by 2 over 2 or x over x? Aren't we changing the equation? Well, think about it. What's 2 divided by 2? That's 1. So all we're doing is actually multiplying this expression by 1 to create an equivalent rational expression. X divided by x is 1, so we're just actually multiplying this expression by 1. So these are equivalent rational expressions. Now pause and practice. I want you to create your own equivalent rational expression for 4 over 10 and x squared plus 2x divided by 2x. Okay, so again, I can't give you every single equivalent rational expression, so I'm just going to multiply by 2 over 2. 8 over 20 would be an equivalent rational expression. X squared plus 2x over 2x, multiplying the top and the bottom by 2. As long as you did your math right, you'll be correct. So 2x squared plus 4x over 4x is an equivalent rational expression. Now, we also need to be able to determine if two rational expressions are equivalent. Well, how do we do that? Well, we kind of use the same concept. So, are 9 over 3x minus 1 and negative 18 over 2 minus 6x equivalent rational expressions? Well, remember what we did. We multiplied the top and the bottom by the same number. So what did we multiply this top number by to get negative 18? Well, there's two different ways that we can do this. We can kind of use logic. So 2, 9 times 2, or negative 2 is 18. Or we can take this number and divide it by 9. So negative 18 divided by 9 is negative 2. Now, if we multiply this denominator by negative 2, are we going to get 2 minus 6x? Well, let's see. Negative 2 times 3x minus 1. Distribute it. Negative 6x plus 2. Well, what we need to realize is that these are the same number. They've just been rearranged. So yes, these are two equivalent rational expressions. The first rational expression has just been multiplied by negative 2 in order to get the second rational expression. Let's try that second example. So 2 minus 2x divided by 4x has turned into x minus 1 divided by 2x. So what I always do is I look for the simplest piece. So 4x is the simplest. How do we get 4x to be 2x? Well, rational expressions don't have to be multiplied by the same number. They can also be divided by the same. So 4x divided by what would equal 2x? Well, that's divided by 2. So what happens if we divide 2 minus 2x by 2? Well, it should equal x minus 1 if these are equivalent. If it doesn't equal x minus 1, that means that these aren't equivalent. So 2 minus 2x would be 1 minus x. Okay, so it looks like when we divide it by 2, it equals 1 minus x, not x minus 1. Therefore, these are not equivalent. In order for these to be equivalent, we could also work the other way. How can we make 2 minus 2x into x minus 1? Or x minus 1 into 2 minus 2x? Well, we'd have to divide by negative 2. So since these two numbers are different, this is not an equivalent rational expression. So you need to be able to work forward and backwards with these in order to determine rational expressions. So multiplying and dividing, looking for those simplest rational expressions that we can change. And that's it for chapter 4.1. So you need to be able to say, I can use simple rational expressions to solve word problems, I can state non-permissible values, and I can determine if two expressions are equal by multiplying or dividing by the same number on the top and the bottom. All right. If you have any questions, please let me know. Otherwise, move on to 4.2, and I will talk to you soon.